Hello, my name is Dylan Shane, and I'll be teaching lesson 10.1 on confidence intervals. As we learned in chapter 9, because of sampling variability, the statistic calculated from a sample is rarely equal to the true parameter of interest. Therefore, when we are trying to estimate a parameter, we must go beyond our statistic value to construct a reasonable range that captures the true parameter value. Confidence interval for a parameter have an interval which estimates plus or minus the margin of error, and a confidence level C, which gives the probability that the interval will capture the true parameter in repeated samples. Conditions of sampling distribution of p hat are it must have an SRS, the population is 10 times greater than the sample size, n times p is greater than or equal to 10, and times 1 minus p is greater than or equal to 10. Conditions for sampling distribution of x bar are it must be an SRS, it must have normal distribution or n is greater than or equal to 30, and the population is 10 times greater than the sample size. If an SRS of size n is chosen from a population with unknown proportion p hat, then a level C confidence interval for p hat is p hat plus or minus z star times the square root of p times 1 minus p over n. If an SRS of size n is chosen from a population with unknown mean mu, then a level C confidence interval for mu is x bar plus or minus z times the standard deviation divided by the square root of the sample size. To find z star, you need to use table B. So you go down across the bottom to find what confidence interval you are looking for, and then just go up to find the value that goes with it. When we estimate a parameter, we would like high confidence but also a small margin of error. This margin of error formulas are z star times the standard deviation divided by the square root of n, or z star times the square root of p times 1 minus p over sample size. To lower the margin of error, you can increase sample size, decrease confidence interval, or decrease variability by looking at a subset. When solving a confidence interval problem, you have to use an inference toolbox. The first step in the inference toolbox is to ID the population of parameter, who or what, choose procedure and verify, calculate. You can either use the formulas given or a calculator. And the fourth step is to interpret it in the context of the problem. This is an example of putting it all together. A manufacturer of high-resolution video terminals must control the tension of the viewing screen to avoid tears and wrinkles. The tension is measured in millivolts or MV. Careful studies have shown that when the process is operating properly, the standard deviation of the tension reading is 43 millivolts. Given a sample of 20 screens with x bar equals 306.3 millivolts from a single days of production, construct a 90% confidence interval for the mean tension mu of all the screens produced on this day. The first thing you should do when solving a problem like this is to take all the stuff the problem gives you and write it down. The sample size is 20 screens. X bar equals 306.3. It tells us to test for a 90% confidence interval, and the standard deviation is 43. When you see standard deviation in a problem, we automatically assume that we are doing an X bar problem. After you write everything down, you then do the inference toolbox. The first step is to ID population and parameter. The population is the high resolution screens, and the parameter is the mean tension. Step 2 is to choose procedure and verify. This is a z-interval problem, and we are testing for sample means. We can assume it's an SRS, and we can assume that it's normal distribution because it says it in the problem. Step 3 is to calculate. The formula that we use is x bar plus or minus z times the standard deviation divided by the sample means. So the x bar equals 306.3 plus or minus 1.645, because that is the z value when you use 90% confidence interval, times 43, the standard deviation, divided by the square root of 20, which is the sample size. When you put that into the calculator, you get 290.48 and 322.12, and that's the confidence interval. The other way you can do this problem is to go on the calculator, hit stat, go over to test, go down to z interval, enter the standard deviation, the x bar value, the sample size, and the confidence interval, and enter, and you will get the same confidence interval that you did by calculating using the formula. The last step is to interpret in the context of the problem. So you say, I am 90% confident that the true mean of the high-resolution video screen's tensions will be between the intervals 290.48 and 322.12. And that's it. That's how you do confidence intervals by the formula and the calculator. Thank you.